Welcome, everybody in the lecture hall. Welcome, everybody on Zoom. Welcome, everybody been watching us for the future, preparing for the exam. So today, if we manage to get the air channel open, yes, so thank you very much. So today we are going to continue discussing the performance at large scales, and then I will continue and proceed to document stores, which is the next step. This is kind of a parenthesis because we're not looking at a new piece of technology here. It's just some high-level considerations on performance. So I already told you last time that there are 4 sources of bottleneck, typically memory, CPU, disk I/O, and network I/O. This is basically the abstraction level for us database people, the way we think of hardware. We just kind of simplify it and abstract it away to these 4 things. And all of that, all of the work on performance comes down to one of the 4. And we saw that whenever you have a problem of performance, meaning that it's too slow, and almost all of you will at some point have this sort of problems that your query is running too slow. For example, it might be problematic if you have a website that people are visiting. After 5 seconds, people are gone. So you really need to make sure that you return ideally within a few milliseconds, but at least less than a second. And so you need to understand what's going on. So typically, one of the 4 is going to be the bottleneck, and you should try to fix it. So we try to quantify what's going to happen if you manage to find the bottleneck and fix it. One of the aspects of fixing a bottleneck is to parallelize. So this is the case of disk I/O, right? If you have disk I/O issues and this is your bottleneck, then you should be using MapReduce of Spark and go to more machines, because then you spread reading from disk over plenty of machines. And then we can try to quantify the performance improvement. So as a rule of thumb, I gave you last time the formula for that. It's basically the time it used to take divided by the time it now takes. And that gives you the performance improvement. For example, if it used to take you 3 seconds and now it takes you only 2 seconds, that's an improvement. And the quantification of this improvement is 3 divided by 2, old divided by new. And that gives you 1.5, which you can reformulate as a 50% improvement, right? So I assume you're comfortable with probabilities using that way, right? 0.9 is 90%, 1.5 is basically 150, so that's plus 50%, and so on, right? Okay, so this is the idea. Now, if you apply this to a setup in which you find out that part of your code is parallelizable, but not all of it. Some parts remain sequential, so that you cannot parallelize. But let's say that 30% of your code, 30% of the time, you can actually parallelize. And when you parallelize, you have a speed up of 2, meaning you take half of the time it used to take, but only on the parallelizable parts, right? So maybe you spread it over 2 machines for that 30%. Now, the speed up of 2 is only on the parallelizable part. So obviously, you're not going to get an overall improvement of a factor of 2, right? It's a common mistake that some people make, right? It's like I doubled the number of machines, it's going to have the time. No, because this impact of doubling the number of machines only have a partial impact on what you are doing. So let's say it have a partial impact on only 30% of your workload, then there is this magic formula over there where you divide 1, that's what it used to take. And now the new time, of course, up to a constant factor, is 1 minus P, so and plus P divided by S. So P is the part that is parallelizable, so in that case 0.3, 30%. So you remove the 30% and you add back half of that because you've improved the runtime, right? So what you get is this. And now you notice that a speed up by a factor of 2, which is having the time it needs, right? A speed up by a factor of 2 only on the 30%, the overall improvement now is only 18%. That's much less than the factor of 2. A factor of 2 is plus 100%, right? So now we are down to just 18% of improvement on the overall workload. So you need to be careful about that when you parallelize, it's always going to be part of the workload that gets parallelized, and the overall speed up is going to be a bit less great. So obviously, if you have a situation in which you can parallelize only, let's say, 10% or 1% of your workload, it's not worth it. And if that's the case, it means probably your bottleneck is somewhere else than there. All right, so that's just the word of warning. Now, this is called Amdahl's law. This is based after somebody who came up with that law, discovered that law. The problem is that there is a competing law that's called Gustafson's law, and Gustafson tells us, no, that's not how you compute this improvement. No, it's not with this formula right here, 1 over 1 minus p plus p over s. It's with 1 minus p plus sp. In the same setup, right? 30% parallelizable, and now I have a speed up of 2 on the parallelizable part. Now, if I apply this formula, I find something different, right? 1 minus the 30% plus 2, the speed up on the part parallelizable. Now I get 1 plus 3, which means an improvement of 30%, right? I'm 30% better, and Amdahl was saying it's 18, and Gustafson is saying it's 30. Who is right? Right? We kind of have, these are the two persons, right? So we need to understand why they are in fact both right. So how can you both be right on plus 18% of improvement and plus 30% of improvement? It's because they are not talking about the same thing. What Amdahl is talking about is you have a certain problem to solve, like, I don't know, a 3-sat on some formula or something, like some complex problem to solve. And for this specific problem, you manage to speed up the parallelizable part and so on and improve, and then you get 18%. Then this applies. But why is Gustafson different? It's that he thinks in a different way. What typically happens if you're pragmatic in reality, what happens if you manage to improve the performance of a problem, people are going to just be solving more problems. This is exactly what happens in reality. You think you solve the problem by making it more efficient, people are just going to use it more. And Gustafson is considering exactly this, is that if you manage to improve 3-sat by a factor of 2, then you're going to solve it twice, one for a formula and a second time with another formula. So what they held for constant in the case of Gustafson is a constant computing power. You consume the same power in the cluster, but you solve more problems with that same power. So what Amdahl is saying is you're going to be 18% faster solving one problem. And Gustafson is basically saying you're going to be solving 30% more problems with the same resources. Okay, for whom is that clear? All right. And by the way, this is useful insight for policymakers, because when you make policies like this, it has an impact and it can have unexpected consequences. All right. So now a few concrete points on how we tune things a bit more concretely, just a few tips and tricks to help you. So first, something that I already told you, if your problem is the disk I/O, you want to scale out, right? You want to scale out the number of machines. This is the preferred solution to scaling up to just a bigger machine, generally, because this is not linear. The cost of a bigger machine is not linear in the resources, but the cost of buying more machines is linear, right? Of course, imagine there is enough supply. All right. So scaling out is generally better than scaling up. And now we know that this is specifically in the case of disk I/O bottlenecks. Now, there are still cases where just adding a bit of memory or a few more cores on the machine does the trick, right? And in fact, recently, some people have started noticing that in some cases, you can actually just pick one bigger machine and it does the trick for many problems, right? So there has been a tendency to have a bit less machines and to have more memory and more CPUs on these machines, right? Just as a rule of thumb. But this probably also comes from the fact that the cost of a single core and the cost of 1 GB of RAM has a bit gone down, right? So it's also because of the evolution of the technology, right? And then you see all sorts of interesting things that are happening, right? Because some people try to fit all the data in memory. So what they do is that they buy plenty of machines in such a way that you're loading your entire database from disk into the memory. 100% of the data is in memory. Then you don't have anything to read from disk anymore. And this actually works quite well. It's called in-memory databases. So this is an interesting trend. What some other people are doing is that they're swapping the disks from HDDs to SSDs, right? Which have better performance. They're a bit faster. And somebody was actually at the end of the lecture last week came to me and said that now SSDs are actually better in orders of magnitude than what I gave to you last week. I'm more used to HDDs, mostly because they are cheaper usually. That was a good point. It's that now you can go well into the gigabit per second, gigabyte per second bandwidth in reading from an SSD, right? Okay, but it's the order of magnitudes that matters. All right, scaling out, scaling up. But there is something even better than scaling up and out, and it is scaling out, but even better than scaling out, even better than that. Yes? Writing better code, exactly. Writing better code is the best thing you can ever do. Writing better code. And in fact, and that's a concrete piece of advice that is very pragmatic, is that if you're trying to query a data set that is 10 terabyte or 100 terabyte or 1 petabyte of data, you will go through a lot of trials and errors, right? You write a query, it doesn't work, you need to try again, and so on. And the problem is that if you need to spend the night running the query and you can only fix one thing every day, you're going to need 1 year to solve the whole thing. In fact, this is exactly what people were experiencing in the 50s and 60s, right? Here at ETH, you were using punch cards, and every time they needed to go the following day, even sometimes more than that, to get the result. So basically, this is problematic. And so what you typically do is you take a subset of the data. You have 100 terabytes, fine. Just sample, let's say 10 gigabytes of that, just 10 gigabytes, or even just 1 gigabyte. Copy it over to your local machine, your laptop, right here on your laptop. And then try to run the code and try to improve it on your laptop on this 1 gigabyte. Maybe it's going to take you 1 minute. Try to improve maybe 50 seconds, 40 seconds, 30 seconds. It's going to be much easier to iterate on your laptop with this smaller one. And when you're done, try again with what you came up with, but now on the cluster. And now magically, you might go down for 10 hours to just 4 hours. But the way you did that is just by writing the better code on your laptop, and this is a common technique. It's also applying to the exercises, right? Sometimes we give you larger data sets that might be a bit long to process. Just take a smaller part, right? In the great language game, we have, I think, 2 gigabytes, more than 2 gigabytes of data, 16 million games. Then you can just take a subset of 1,000 or 10,000 of them, right? And just work on that to build your query, and then you get almost instant answers, and that's it, right? So it's a concrete piece of advice. Now, how do you write the better code? What should you consider? Well, there are a few tricks. So I'm going to go a bit through each one of these resources right here, and I'm going to start with memory. So typically you have tools, right, that help you. And these tools are usually easier to use on your laptop, right? So this is why it's really worth using your laptop. So typically, when you use, I used it a lot for Java, but I imagine it's available in many languages. There are profiling tools that show you while you execute your query. So try to pick a workload that is long enough to last maybe 1 or 2 minutes, just so that you have time to observe a bit. If it's too little data, it finishes immediately, so you don't even have time to observe. But if you take something that lasts for a few minutes and run the profiling tool, you see the usage of the memory in real time. And you will see if you have, let's say, 32 gigabytes on your machine, goes up to 10 gigabytes, 16, maybe you see it goes all the way up to 32 and start swapping to the disk, right? That's useful information, because that means you're using too much memory. And that tells you in your code, you can actually improve. For example, you might have objects in Java or Python that have fields that you don't use. Or maybe you have fields that are redundant, meaning that you can derive these fields from the value of other fields. Try to reduce to the bare minimum that you need in the objects, not any objects, those that you have billions of times. The objects that basically are created for every one of the records in your data set. So try to find the class that is instantiated billions of times and try to remove fields in that class. That can have a massive impact. It can reduce, let's say you were using 10 gigabytes, brings you down to 7 gigabytes, just removing one field sometime, right? So this is a good thing. Sometimes you find more memory efficient data structures, right? You have a lot of ways, for example, maps, sets, and so on. You have multiple implementations of that. And depending on the use case, maybe the version using hashes or the version uses trees, one of them might be more memory efficient. It might depend on your use case. But basically, you can swap it if all you need is the API, right? A map is a map. So if you only rely on the fact that it's a map, it shouldn't matter if it's a hash or a tree map, right? Then you can just swap the underlying class. So these are examples here: tree map, hash map, array list, linked list. These are many ways of having a list in Java, right? All right, then you have sometimes redundancy, right? So that's what I said, you store multiple times the same thing. Sometimes redundancy is useful, but it's useful if your bottleneck is the CPU. Then having redundancy might be useful, right? But if your bottleneck is the memory, then you don't want redundancy. You want to store less in your memory. And also, you need to be aware that when you use inheritance or RTTI, which I never remember what it means, it's a runtime type inference or something like that, if I remember correctly. It's this whole mechanism by which you have a subclass, and then the methods are automatically those of the class you have dynamically, right? Even if the static type might be a superclass. But this is consuming. This consumes memory. It creates additional structures in order to support subclassing. And this is why some companies completely ban subclasses. They forbid it. No subclasses, interfaces, abstract classes, but no subclasses. So there are reasons for that. And it might run contrary to what you learned in object-oriented programming, but in the context of big data and repeating billions of times, you want to avoid all of that. It's very costly. If your bottleneck is the memory, right? So there's this if. Now, maybe your bottleneck is not the memory, maybe your bottleneck is the CPU, right? And that you see because the memory is not completely used. Maybe you have 32 gigabytes, but only 10 gigabytes is used. But you see that your CPU is running 100%. There are profiling tools that you can use, that you can launch at the same time of your program in Java, for example, and it will tell you the time it spends in every piece of the code, in every function, every method. It tells you that many seconds, that many percents. You have the exclusive time that is really spent within the actual implementation. And then there is the recursive version where you also consider the calls of the functions while you wait for the input. It is extremely valuable because you can actually gain insights. And very often you would be surprised. When you execute and it's slow, it feels like you have a mountain to climb, right? How do you make it faster? Then you execute the profiling and you notice 50% of your time is spent in a completely stupid place, right? And you just realize sometimes instantly, oh yes, I can just rewrite this. And then I got an improvement by a factor of 2. And it happened to me, to some of my colleagues. This is an awesome feeling to have when you do that. You profile your code, you find things like that, and sometimes in just a few seconds, you get improvements like this. So this is how it works. You can use these profiling tools. It might be that you're calling too many methods, meaning you have too many functions that are too small, and that's also something tempting to do in object-oriented programming. But if your methods are too small and there are too many method calls, this is consuming on the CPU. Not always, of course. There are optimizers at compile time that are able to actually inline the method calls to avoid that. But in some cases, it's not possible, right? And then you have what I call a spaghetti bolognese of one-line functions in your code, and that makes it quite slow. It's easy to read, right? It's beautiful from an object-oriented perspective, but it can be slow. Maybe you are also using a method overriding, right? When you have the same method in a subclass, and again, that's a consequence not just in memory, but also in the in terms of CPU usage. And here I'm going to be saying something. I hope there's no people teaching object-oriented programming here, because I'm going to tell you use switch, right? Instead of these method overriding, just use switches. We love them in big data and at large scales. It's avoiding the function call. All right, but again, don't get me wrong. I'm not saying you should always do that. This is in the context of big data, right? In some other context, you want beautiful code for other reasons that are very valid, and then you should still be using overriding methods. Class hierarchies also can be very resource consuming, and we've seen that in some. I chatted with some people who have student projects, and sometimes in the projects we see class hierarchies of a depth of 18 classes. Like there's 18 levels of hierarchies in the classes, and then it's slow, right? And the way you make it faster is by diminishing the number of levels or even making it completely flat. It does mean that the code is going to be less nice than the pure OO methods. And And there will be redundancy in the code. You might copy paste the same code at multiple places, but it's going to be faster. So this is why it's actually something we like when implementing systems. And then there's tinier tricks, like, for example, avoiding instance of casting and so on. If it's just once, that's okay. But if you do it a billion times, then an instance of can be more time consuming than just a switch or testing a value of a field that your hard codes. That might be more efficient, right? And another thing is exceptions. Exceptions consume resources. Exceptions, normally, do not abuse them. Exceptions should be used when there is something out of the ordinary, right? Like a division by 0 or something you didn't expect, then you throw an exception. Do not use exceptions for normal running of the code. Do not abuse them, because the exceptions really take more time. And again, some companies forbid them in their style guide, except if there is an actual error on an actual issue. But do not use exceptions for the normal execution of your program. So these are just a few tricks that are here, and there's many others. But what I wanted to tell you is that programming at large scale is really a completely different experience. And sometimes you have the opportunity of being exposed to that in some of the projects at ETH, right? What about the disk? Well, that is the easy part, because that's when you can use MapReduce and Spark to parallelize, right? So if this is the problem that you have, that you cannot read fast enough from disk, that's easy. But there are other tricks that sometimes can solve the problem just as nicely as parallelizing on a cluster. One first thing you can do is more efficient formats. Do you have an example of that? Do you remember an example I gave you? Imagine I give you a data set. In fact, we give you a data set like that, the Great Language Game, in the exercises, or if we haven't, then we will. It's 16 million objects, 2 gigabytes plus of memory, and all of these objects, it's highly structured, they all follow the same schema. Should I actually store it in JSON when I query them? I have a Frosch im Hals, I think in German. Okay, can anybody tell me that? What is more efficient than storing in JSON if you have highly structured JSON? Parquet, yes, exactly, Parquet. Parquet is going to be more efficient because out of the valid JSON, you can create a data frame, right? And a data frame means that it's the same fields everywhere in every object, so you only store them once, that's the schema. And then in Parquet, you just store the schema once, and then you store column by column in the file format, just the values. This is extremely efficient, and you will see that sometimes you gain a factor of 10. It's going to take just 200 megabytes instead of 2 gigabytes. Depends, of course, on the data set, but this is a great way of improving. You wouldn't imagine what the huge change that it is, because if your problem is reading from the disk, that will make you 10 times faster just because you have 10 times less bytes to read from the disk. Of course, that's assuming you have plenty of queries to run. If you only have one single query overnight, it's not worth spending the time restoring it in a different format, because then you will anyway have to go through it again. If it's just reading it once, it's fine to use JSON, right? But in the case that you have 10 or 20, or maybe you need to reiterate the queries, then Parquet is a very good idea when the JSON is valid. And then you can squeeze it even further with compression. There are, in fact, I think Parquet probably even supports that. At least there are formats who support this. Imagine that you have a column and you're repeating the values a lot in that column. Imagine it's a column with strings and you have countries in there. And every time you store the name of the country, then you can use a compression scheme. It's called the dictionary encoding. You give a number to every country, 1 to 200. There's 200 countries in the world, roughly. And so you give a number from 1 to 200, and you store that number instead of the country. And if you want to push it further, you ask, okay, 200, how many bits do I need for that? 32 bits? No, that's way too much. 16 bits, 8 bits is enough. 8 bits gives you, if it's an unsigned an unsigned byte, sorry, that gives you 0 to 255. That's more than enough for the countries. So now you went from potentially, I don't know, a string of on average 10 characters, 10 bytes, you squeezed it all to just 1 byte, right? It's a factor of 10. So this is the sort of compression that you can get. You don't need to do it yourself. Typically, you have an API to switch the compression on. And there's plenty of research done about that. For whom does that make sense? Right? So you try to squeeze all you can. And there is something else that I probably have. Yes, I have it right here, so I'm going to not say it right now. Something else that helps to compress is to use a binary format instead of a textual format. And typically, Parquet is also a binary format. So it's going to be less easy to read it by a human, of course. You need a computer, but it takes less space than the raw syntax. All right, so each has their advantages, but the binary format is more efficient if you want to squeeze performance out of the system. Now, there is another general way. The reason I put it here is that it's not just about the disk, it's also about the memory, it's also about the network. In fact, it has an impact everywhere. If you naively run a query, where does the data flow? It's going to be read from the disk, then maybe you will navigate through it from memory, it's going to be copied over, it's going to be maybe flushed and compacted on disk, then it's going to be shuffled and sent over the network, and then again and again and again, right? And then written back to, the results are written back to disk. Well, in some cases, if you think about it, imagine just as a mental experiment, imagine that you take your input data, let's say it's Parquet, and you copy over the Parquet file to another one, but you drop a few columns. Let's say you drop 3, 4 columns of that file, so you get an even smaller file, and then try to run the query again, and it works. Well, that was because these columns were useless. And it is the case that many queries will not even touch all of the input data. They will ignore part of the input data. So what do you do in this case? Well, if you don't do anything, you're just going to bring over and carry over these useless data multiple times. But very often, you can detect as an optimization. So sometimes Spark is going to do it. Sometimes you need to help the system a little bit. But you can do what's called a push down. For example, if your query is a selection followed by a projection. So you first select records, and let's say you have 100 keys in your JSON object, and then you select some of these objects, and then you project to just 2 columns. Then that's inefficient because you're going to be doing your selection using these objects with 10 keys, right? But if you're smart, you can figure out we can push down the projection. It means that I'm going to commute, I'm going to swap the selection and the projection. And what I'm going to do is that very early, I'm going to get rid of these 8 columns that I don't need. And then I run the selection on the data with only 2 columns. It's going to be much faster. But there's something even better. These 8 columns that you don't need, you don't even need to read them from disk. And in Parquet, you can do that. Parquet, since it stores column by column physically, if you say when you open the Parquet file, I only need these 2 columns, Parquet is not, your hard drive is not even going to bother reading the columns you don't need. So it diminishes even further your disk I/O. This is called a push down. You can do it with projections, but you can also do it with pre-filtering. You can already filter the data early if you know that some data won't be needed. So with pushing down a selection, sometimes you can pre-aggregate. Oh, wait, we've done that. That's the combine function in MapReduce. That's a pre-aggregation. We push down the aggregation all the way to the mapping phase. So there's a déjà vu to this, right? So pre-aggregation. But again, the one name to remember is push down. You push down all you can to as early as possible to get rid of as many bytes as you can, and it's going to make the shuffling and the queries more efficient. For whom does that make sense? All right, awesome. And again, sometimes the system will do it for you. In fact, if you use data frames in Spark, it's going to be automagical. It will just happen. You will just notice that it's faster. And in some other cases, the system is not able to detect that because it's in fact a very hard problem to solve generally. Then you can do it yourself. You can add in your code a manual projection because you know you don't need the columns, and you will notice that it becomes faster. All right. If it doesn't become faster, then it means that it was already doing it automatically. And another way to avoid the network I/O is to batch process. That has to do with latency. If you don't batch process, meaning that you execute very small tasks of very few objects, then the time you spend switching between the tasks is too much. You lose time in latency waiting for the bytes to arrive. By grouping the task into reasonably big enough tasks, you're spending more time transferring data than waiting for it. So that's called batch processing. Okay, that's also the reason we have this flushing and compaction in HBase, in MapReduce, and in Spark and many other systems. Okay, and so you need to keep shuffling to a minimum. Shuffling is when the data is just shipped all over. Why? Because shuffling is quadratic. So anything you can do to reduce the amount of data shuffled around, that can involve pre-aggregation, pre-selection, pre-projection, and so on, then do it. Keep shuffling to a minimum. You can also avoid shuffling if, for example, you sort on the same key that you grouped by. That also removes the shuffle, right? So it's the kind of thing, if you see in your mind, you're able to imagine the data flow, then you can really go a long way in terms of optimizations. So now you can tune also the configuration of Spark. I've already told you a little bit about that, the parameters you can enter. For example, imagine that this is my hardware. Somebody gave me a data center. I'm very happy about that. It has 8 machines and I have 16 virtual cores, so that's including hyper-threading, and 128 gigabytes of memory per node. What do I do with this? So one possible strategy is to have one executor per machine. An executor is a container for Spark, remember? And I give it 15 cores. Why not 16? Because I want some breathe, right? I want the machine to breathe a little bit. So only 15 out of 16. 100 gigabytes, again, less than the total to give a bit of air to the machine for the operating system and the rest to work. And then I have one executor per machine. That's approach number one. There's the opposite extreme approach where I have one executor for each core. So now I have 15 executors per machine, one core per executor. And then I must allocate less memory, of course, 8 gigabytes. 8 times 15 is normally 120, so I'm still below the total amount, right? Maybe with a bit less air. I could have done 7 gigabytes or 7.5 gigabytes, all right? So this is basically large executors. These are smaller executors. These are the two extremes. Well, in fact, I like it in the middle. The rule of thumb that I have, but again, that's mine and some other people might see it differently, is that I like to take the square root of the number of cores, roughly. So if I have 16 cores, I think, okay, 4 by 4. Now, if I want to give some air, I will go down to 15. So the closest I get to some square is 3 by 5, basically. So I can have 3 executors of 5 cores, 5 executors of 3 cores, and then I allocate a bit more memory. Usually, this is what I found to work the best, to go for the square root, right? For whom does that make sense? Right? So just to give you an intuition. So the idea is that if you do this, it restricts the data that goes into a task to not use more than 8 gigabytes to be processed. That's very small. But if you have slightly larger executors, one of the tasks, there's 3 at the same time in the same, but one of the tasks might be taking, let's say, 20 gigabytes, while the others take 5 and 5, right? So it gives you a bit more flexibility. Having one single executor basically pushes the system a bit to its limits in several aspects, right? So I don't want to go into the details of that, but basically this is a bit too much, right? So the right mix is in the middle. Okay, al dente. This is the al dente approach to Spark. Now, this is the slots, right? We have slots here with every core gives you 1 slot to execute tasks. Now, how many tasks should you have? Here, I'm repeating myself because I already told you you should have more tasks than slots, a multiple of them. Why? Because if you say, okay, 1 task per slot, you might hope for this. The problem is that this is not going to happen. This is going to happen. One of the tasks is going to take longer and the others are unused. So this is why you need to have more tasks and let them distribute dynamically like this. It will even things a little bit out. But do not push it, because if you have 2 small tasks, what problem do you run into? Starts with an L. Latency, exactly. Then you have latency issues. So do not push it too much. Let's say 3 to 5 times the number of slots for the task is kind of nice, right? But of course, people have different preferences, but this is kind of a rule of thumb. Now, Well, I don't know what I meant with that slide because I already told you, yeah, you can have a network bottleneck, obviously, and the network bandwidth is limited. So I think I'm just repeating myself in here. I'm not sure why I put that slide. Anyway, and of course, some of you, and because you're master students in computer science, you are the engineers of tomorrow. I'm pretty sure some of you will belong, maybe you will be hired by Databricks or Snowflake, or I don't know which company is building technology like that. Maybe some of you will found your own company and you will build a better Spark. Maybe you will fix problems that we didn't have. Like, for example, in Spark, we don't know how to execute a job in a job, right? I cannot nest job. Maybe some of you figure it out and then you have a completely new product, right? So, there's a lot of you, I'm pretty sure some of you will be building systems like that. So this is why it's important to know the history and how the existing systems work. Now, this brings me to tail latencies. Turns out that this year, because you are so brilliant and you actually asked about it, yes, go ahead.
I have a question on the strategy slide. So a few slides back. One more. Yeah, here. I see that in all of the examples, it's like a symmetric type of strategy. But what about if you try to have a bit of a, like some machines with, for example, which could execute tasks which are more memory intensive, for example, and others which are more IO, so like more cores. Have you seen any strategies like this, for example?
I could imagine that you will find use cases in which the workload is unevenly distributed and you want to do it. In these use cases, it would make sense to try to come up with an architecture like this, but it has a cost. First, it has a design cost because you will need to actually build a system that does that. So it's engineering work. The problem that you might have is not going to be a technical problem. It's going to be a problem with the CFO. The CFO is going to ask you, if I'm hiring people to do it, how useful is it going to be for the company? And this has to do with how general purpose is your system. And so one of the motivations like this, of a system like this, is that it's simple to build and it's kind of general purpose. It fits a lot of use cases. Now, you might have use cases that are actually might be core to your business as a company, and then it's repetitive, it's always the same way. Then you might want to invest efforts in order to build a system like that. Maybe some people did. Actually, if you take the example of running machine learning stuff on top of Spark, at the very beginning, it was just naively using Spark. There's something called Spark ML, right, that allows you to run machine learning workloads. And so in the very early days, they were just like implementing it and running on Spark. But now, the machine learning people are designing their own systems in order to do it, highly optimized for machine learning, aware of the machine learning algorithms. And you even have people who build hardware for machine learning, right? That is very good at multiplication and addition. So this is really, I would almost say it's a general purpose / usefulness to the business consideration, and also a simplicity versus complexity consideration. Again, it's a great idea, but you need to quantify how much it would cost you versus how it will help you and how often it will help you.
But you would be able to use such a strategy in the same cluster. I think that's what I was trying to get to.
Yes, absolutely. So you could, and I imagine it might be that people build systems like this. What I'm saying is that it's more complex to build than something that is highly homogeneous and simplified. Right. Thank you. Any other questions? Right. I'm going to move on to the tail latency. So I was saying you're brilliant. And it's actually fun to teach with you because you already brought it up very early. In fact, when you talked about MapReduce and asked like what happens is there always going to be a straggler if I improve the code and so on. So you already kind of know about this. So in an ideal case, and you did your job of having more tasks than slots, maybe you have 5 more tasks than slots, and you notice this, in that case, I only have 5 slots, right? So this is pretty much how things work. So there's nothing really too surprising about it. We just improve the code in order for this to work as fast as possible and without wasting hardware. Now you scale you scale out to more machines, more slots, and then you might hope for this to happen, right? You have more tasks than slots, and that should actually pretty much distribute in a way like this. The problem is that in reality, this is what you get. And I'm talking here like scaling to thousands, 10,000 of machines, maybe even 100,000, maybe you spread over data center, and then you end up like this. You have all of your slots that complete the task in a reasonable amount of time, and then you're always going to have that one slot that just takes forever. And so you would be very tempted to say, okay, let me optimize this. Let me add more tasks. Let me apply all of the things that I have been taught in the big data lecture. Let me improve the code and so on and so on and so on. And then you execute again, and bam, that happens again, right? The problem you're having is that it's another problem than just performance or bottleneck. It's a completely different problem that's called tail latency. And that actually comes back to what happens at the very low level on the machines, because this is running on the machine, right? Information is physical. So the resources are shared on the machine. And on the machines, you have operating systems, Linux, Windows, macOS, and so on. So you have an operating system that runs. The resources you're using are shared. The data flows over the network switches, but they are shared. So they are all the same switches, right? You have a distributed file system and so on and so on. And so that means that on all of these machines, you have all sorts of stuff that I don't really understand because I'm a database person, but somehow on hardware, you have hiccups, you have all kinds of background demons that are running and so on and so on. You have queues, you have power consideration, the cooling, garbage collection going on in Java. When it runs smoothly, you might forget about it, but then it might actually create interferences, the energy management and so on. And all of that leads to that kind of things to happen. Basically, you're going to have a problem in a queue or with energy or whatever, and then on one of the machines, statistically, you're going to be completely blocked, and like for a very, very long time. And that has absolutely nothing to do with how you're building your query. It's on the hardware, low level, some of the stuff that we actually abstracted away. And here it comes back to bite us, right? So what do we do about it? So let me take an example just to quantify the thing. So imagine that I'm using my SLA with the 9s, right? So let's say that my typical latency would be 10 milliseconds, meaning the time that it takes for a task in that context, the different definition of latency. But let's say that I'm guaranteed in 99% of the cases, 99%, I finish in less than 1 second for one slot. Let me talk slot by slot. I'm guaranteed that a slot is going to be done in less than 1 second in 99% of the cases, and in 1% of the cases, taking forever, okay? Now, if I have a single node, then that's easy, right? In 99% of the cases, it's going to take less than 1 second, and in 1% of the cases, more than 1 second. It's just tossing a coin, or well, in that case, you would have to toss 7 coins to get that level of precision in probabilities, but that's basically random, right? You just produce a random result. So in 1% of the cases, it's more than 1 second. In that case, it's no big deal. You just do it again if it happens. But then you might think, okay, what happens with 10 nodes? And with 10 nodes, if you compute, it's the probability that one of the nodes takes more than 1 second. If you remember your probability theory, that's 1 minus p to the power of the number of nodes. That's the OR formula. If it's and, you multiply, but if it's OR, it's 1 minus p to the power of n, which in that case gives us 1 second, more than 1 second in 10% of the cases, that at least one of the 10 nodes is going to take more than 1 second. 100 nodes, now it's 2/3 of the cases I'm going to have the issue. That's already a lot, right? And now with 1,000 nodes, it's almost guaranteed I'm going to have the problem. In fact, I'm going to be winning at the lottery if I don't have the problem for that kind of probability, right? So basically, if you have a large number of nodes, you cannot escape it. There's no way you can actually escape that, right? So you might say, okay, but then let me try to make things such that my probability, the parameter p, diminishes. Let me assume now I guarantee 99.99% of the cases, right? How could it fail, right? In that case, I'm surely going to get better numbers, right? The problem is that as you have 2,000 machines, you're already hitting the problem again with just in 20% of the cases. Yes? It's not like that. That would be too simple. That would be too simple. This is unpredictable. Yes, so absolutely. People do it, in fact, right? You would identify in a data center some machines that do not work and you switch them off, but it still doesn't solve your problem. There will still be that kind of things happening, right? You deserve the break. I'll finish tail latency right after the break and then move on to document store, right? So see you at 3:15. Thank you.